All right, in this video we're going to look at graphing some space curves using CalcPlot3D. So we've graphed some other things using this software before, so I just want to go through how to get a space curve graph on here. So I don't really want to see the graph that's on here, and I also don't really like the box that is the default setting on here. So I'm going to go to these little boxes along the top have some options for changing the view. The second one here is the one with the box. So I'm going to uncheck that. Oops. I'm going to uncheck that one so that the box goes away, and then re-click that so that that menu goes away. I also don't want to see this surface. So there's a couple ways I can get rid of that. One is just to uncheck the box where it's checked that it graphs that. I can also just click the X over here on the right side so that that's just completely gone from my choices over here. All right, and what I want to add to the graph now is a space curve. So there's this bar that says add to the graph, and then this choice of things that you can enter here. So we want to enter a space curve, R of t. And so when that comes up, you see we've got these boxes to enter parametric equations for the space curve. And the default one that comes up here is just a circular helix. You should be able to recognize that at this point. That goes up the z-axis with a period of 2 pi. So t equals 0 to 2 pi will take you through 1 revolution on that helix. We're going to graph a different curve, so I'm going to just type in what I want here, but it is helpful to kind of pay attention to the syntax in the example. The cosine and sine functions, you have to put parentheses around whatever the input is for those functions, so make sure when you type in your own curve that you do that. Okay, so I'm going to graph one that we've graphed before. So for x, we're going to look at x equals 3 cosine of t. We graphed this one by hand before. Y equals 2t, and z equals 5 sine of t. So we graphed that before. That's an elliptical helix. I should expect that the x will go from positive 3 to negative 3, just thinking about the outputs of that cosine function multiplied by 3. The z's will go from positive 5 to negative 5. So I'm going to have to change my scale on my axes here a little bit so that I'll be able to see all that. And the period of these trig functions is 2 pi. So if I want to see 1 revolution of this elliptical helix, I'll want to do a t interval of 0 to 2 pi. I'm going to type that in here. You might notice that I can just type pi for pi. Number of steps is the change in t and how many points it makes. So it'll take the interval 0 to 2 pi and divide by 100. And that's how many points it will plot to make this curve. So that's probably good. You can make that bigger if you want a more refined graph, but then it'll take longer to graph the curve. So there's some trade-off there. I do want to see some orientation arrows. I'm going to put 2 here on orientation arrows. And I mentioned that we do need to change the scale on axes, so I'm going to do that before I graph it. So the x will go from negative 3 to 3. I'm going to go up here to the axes. I'm going to make my x's a little beyond that. I'll go negative 4 to 4 for my x's. To see 1 cycle of this helix, if I look at my equations, the y will go from y equals 0 to y equals 4 pi in that interval of 0 to 2 pi for t. So I'm going to let my y go from, say, negative 1 to maybe 14. 2 pi is somewhere around 12 or 13, so 14 for the y max there should be good. And then the z's will go from negative 5 to 5. So I'm going to just do negative 6 to 6 on my scale here, just so it's not right up against the edge. And then that should be good. I think we should be ready to graph. I'm going to re-click that to make that menu go away. If I check the box here, we should be able to see the graph. And I guess probably I need to say graph, so that since I changed the scale on the axes there. All right, so we see that curve. The default setting is this lovely rainbow, and you can rotate that curve all around. We're going to graph a few more curves on here, though, so I'm going to choose a specific color for this first one, and then some different colors for the other ones here. So you can go down here and choose use constant primary color, and then a default color is chosen for that curve. You can change it. If you click that color, you can change it to something different, but I'm just going to leave this one red. So we know that this is an elliptical helix. If you look at it kind of from the end, you can see that elliptical shape, but notice when you rotate that in space, it looks sort of funny because you're looking at this three-dimensional curve in two-dimensional space here, and so it looks like it's maybe not quite as symmetric as it actually is, or depending on how you have those axes rotated, it might even look like it makes a sharp corner there at the bottom, but you know from thinking about the equations that it does not. It lies on that elliptical helix. Okay, so we're just going to add a couple of other curves to this same graph so we can do a little bit of comparison between those equations. So I want to add another space curve, so I'm just going to go up here and select space curve again and type another one. There's a different default one that came up here, but I'm going to just make some minor modifications to the curve that we had before, and we're going to talk a little bit about how that changes the geometry of the curve. Right, so what I'm going to do here is type essentially the same equation we had before, but instead of having t inside the trig functions, I'm going to put 2t inside the trig functions. You'll notice there I need to be a little careful with capitalization. I had a capital T, but I changed that. I'm going to leave the y equation alone, and I'm just really changing the input on the two trig functions as compared to the graph that I graphed before. I'm going to leave my interval 0 to 2 pi. This one has number of steps 200. I'll just leave it like that. I do want a couple of orientation arrows, and I'm going to use another different constant primary color. So for this one, the default was blue. I'm just going to leave that blue and check that, and there we see that graph. Okay, so one of the things that you want to eventually be able to do is to think about what this graph would be like without necessarily needing the computer or needing to graph it by hand. So you can see here that it looks like on this graph that it lies on that same cylinder, right? If we did some eliminating the parameter between the x's and z's, you'd see that that curve lies on the same cylinder as the red one. But we seem to have two rotations here in that interval 0 to 2 pi instead of just one rotation in that interval 0 to 2 pi. And you should be able to notice why that happened here. I changed the period of the trig functions by putting that 2 inside the trig function. So I made the trig functions oscillate faster or have a shorter period. So they'll make 2 cycles in that interval of 0 to 2 pi, or you might say that the period is just pi, 0 to pi, if you think about period versus kind of frequency of the oscillations here. All right, so eventually you want to be able to kind of recognize that when you see an equation that it's going to make twice as many cycles in the same interval as a different curve. All right, let's look at one more here. I want to go back to, I'm going to add another curve here. So we're going to click add another space curve here. And I'm going to just type this in, and then maybe we'll talk a little bit about what we expect to happen. So I've got 3 cosine t, and 5 sine t. Okay, so as compared to the original curve, what I've changed this time is the y equation. I've changed the y equation here. I'm going to leave my interval 0 to 2 pi. That's up here. That's the same interval I've used for these others. And I'll leave my number of steps 200 here. I'll put a couple of orientation arrows on the curve, and I'm going to use a primary color. I'm going to use something a little brighter here. Let's look at orange here so we can compare that. All right, so when I check the box, we should be able to see this curve. And ideally, eventually, you want to be able to think about what that curve is going to look like without needing the computer to show you for a fairly simple curve like this one. So, all right, so when I look at that, when I check that box, it appears that that curve is right on top of that blue curve. It appears that it's right on top of the blue curve. You can see the orange and blue kind of dashed on top. And if I take away the blue one, uncheck that box, you see that it appears that they're right on top of each other, the blue and the orange one. But the orange one, it's only got about half as much of the curve, it appears, as the blue one does. And so if you go back and think about the equations, the period of those trig functions is still 2 pi. So 3 cosine t and 5 sine t, those both have a period of 2 pi. So in my interval of 0 to 2 pi, I'll make 1 revolution. But what I changed this time is the y as compared to the first equation. And so in that first equation, the red one, remember that our interval there was also 0 to 2 pi, but y went from y equals 0 to y equals 4 pi. So 1 revolution around the cylinder, but y went from 0 to 4 pi on that first one. And on this orange one, the y will only go 0 to 2 pi. If I want to see another cycle of that, I can change my t interval to 0 to 4 pi. And so we see the curve this time all the way there. And the orange and blue curves, if I delete the orange one, you can see the orange and blue curves appear to be right on top of each other. So one of the important things about this example is thinking about, is that orange curve the same as the blue curve? And the answer is kind of yes and no. So geometrically, it appears that the orange and blue curve have the same points, the same XYZ points. So they have the same geometry. If I wanted to talk about how tight the bends were on that curve or how far apart the coils are on that curve, those really appear to have the same geometry. We'll look at some mathematical ways to describe that too. But if you pay attention to the t interval, remember on this orange curve, it took a t interval of 0 to 4 pi to make that curve. And on the blue curve, it only took an interval of 0 to 2 pi. So if t really represented time, the orange curve would have taken twice as long, twice as much time to traverse that whole same shape as the blue curve. And so in some ways, the geometry of the curve is the same, but the orange and the blue curve represent different motion along that path. And that's going to be kind of foundational to one of the things we talk about really in the whole rest of this chapter, is how to mathematically describe the geometry of a curve versus a particular kind of motion along the curve. So you might think about you're traveling the same path, but are you walking, or are you running, are you driving a fast car, are you starting out slow and then speeding up? And so we're going to be able to describe all of those things, not only the geometry, but the particular motion along the path. So we'll look some more at that really throughout the rest of this chapter.